We're going to start with questions on the homework. And looking for which one? Number 3 and number 15. 16. Let's hand back some homework from Caleb Callison. Evan, and here's a Caleb Callison. Evan Beecham. Evan Beecham. Cash Dowers. Jacob Bettis. Dylan Anderson.
You've been sick.
Dylan Anderson. Dwayne Lee. Colton Mashburn. R.J. Darnell. That's fine. Just set it there. R.J. Chad Pryor. Hunter Turnage. Hunter Turnage. There you go. And back to Colton Mashburn. Evan Beecham. Cash Dowers. And Dylan Anderson. Final call for Dylan Anderson. Could y'all pass this around and sign in, please? Oh. What was your name? Ryan? Nope. All right. Number 3, what potential difference is needed to stop an electron that has an initial velocity of 6 times 10 to the 5 meters per second? Okay. We have an electron. So its charge is minus 1.6022 times 10 to the minus 19 coulombs. And its mass is, somebody help me out. Kilograms. And it has a velocity of 6.0 times 10. What is it? 6.0 times 10 to the 5, was it? Yeah, meters per second. Who would offer a suggestion of where to start? Anybody?
Start by finding the potential difference.
Nope. Good guess, but not this time. First thing we could find out right now is what's its total kinetic energy? And once we get that, we end up with kilograms meters squared per second squared, or some number of joules. What's your name?
Dylan.
Oh, excellent. There we go. You sign in?
No, I didn't.
That gives us a number of joules. We know how many joules we have, and then we have some number of joules times 1.6022 times 10 to the minus 19 EV per joule. And that will give us the energy of our electron in EV. And since it's one electron, it needs that much voltage. That's the potential difference it needs to stop it, to decelerate it from its velocity back to zero. Everybody see that? Remember, EV is the potential difference, the delta V, times the total charge. That's the EV of a particle. If you have a 6 Coulomb ion, or a 6 times 10 to the minus 6 Coulomb charge particle moving, accelerated through 15,000 volts, then you get 15,000 times 6 times 10 to the minus 6 coulombs, and that's how many EV you have. And this,
I don't see what you got. I mean, I follow you. What you wanted to find through. What's the part you just moved down there? I don't see how you got that. Like KE times joule.
okay,
Why?
kinetic energy. No, this is just the number, the result of this calculation. That's all I wrote. I just wrote the KE here because there's a number there. Didn't punch in the number in the calculator to get this number, but that gives me a number of joules, which is the energy of that electron.
And then, whatever, I thought you just, there was a number that you times to get your volts, electric volts.
Electron volts. Exactly. 1 electron volt is equal to 1.6022 times 10 to the minus 19 joules. That's your conversion factor. And that's why here I multiplied. I guess I did do that. Did I do that backwards? Which is it? 1 EV is equal to that many joules. So I did it backwards here. You're right. We have some number that number of joules times 1 EV per 1.6022 times 10 to the minus 19 joules. And thanks for catching that. That's that I did do that backwards. That will give you the energy of that electron in EV, which is also the voltage necessary to dissipate that much energy, or to counteract, to stop the electron, to bring it back to rest. Okay? I mean, as long as you're talking about an electron or a proton, then the EV is the voltage.
Well, I thought
Say again. No, ask it.
I'm trying to figure out how to ask it. So you just pretty much divided your kinetic energy by your conversion to your electron volt.
I converted this many joules into this many electron volts. Okay. Let's see if I can. Yeah, that's really that's the best way I can describe it.
Yeah, I get that. That's not bad.
Well, it would be if you punched in the numbers. I just didn't type in the calculator.
Well, see, I guess I just didn't understand exactly what potential difference is.
Potential difference is V final minus V initial. The voltage or the potential at the starting point minus the voltage at the end point.
But it only gives you one velocity.
Right?
Like it just gives you the initial. It doesn't say what it adds to it or.
You get this velocity that you use to multiply, to calculate the kinetic energy of an electron. Okay? Because the kinetic energy is 1/2 mass times velocity squared. So if you know how fast the electron is going, you know the mass of an electron, you can calculate its kinetic energy in joules. Once you know the energy in joules, you can convert that into electron volts.
So electron volts is that's what the problem is.
Yeah, I understand that an electron volt is a unit of energy.
Like all I feel like we're doing there is just like you found the kinetic energy that it had, and then
Yeah, it's really as simple as that. Where? Oh, well, in the you're going to need the potential difference. You're going to need for it to go through to stop, which means you're going to need it to go from positive to negative potential.
I think I get it now. So it's like it's going, and then you got to have the same force to stop it, right?
Exactly.
And so that's why you just converted it, because the electron volt is what's going to stop it.
The electron volt is the energy that will be dissipated by that. An electron volt, and again, this is not standard SI units. So that's why we have to convert to joules to find out if we're given the energy of a particle in electron volts, then we have to convert that into joules to find out how fast it's actually moving in meters per second. And vice versa. If we're given a velocity, then we have to convert that into we have to first calculate the kinetic energy in joules and then convert to electron volts. But 1 electron volt is the amount of energy that an electron, or a particle with a charge equal to that of an electron, the energy it will get, or the work that will be done on it by an electric field across a potential difference of 1 volt. So if you have one electron that's accelerated through 1 volt of potential difference, that electron then has 1 eV of energy. Okay? If an electron has 1 eV of energy, then you would have to pass it through the appropriately polarized potential difference to bring it from that energy back to 0. So you'd pass it through. If it's an electron, it's a negative charge, so you'd have to pass it through a negative potential. Frankly, that's the part I always have to stop and draw out the pictures to keep track of, is the electron going from a positive to a negative potential, or is it going to go from a negative to a positive? And because if it's a proton, it's the same charge, so it'll be the same potential, but it'll have to be the opposite sign. I just have to sit there and quizzle it out when I do that. Is this starting to click with everyone? What would be different if we were doing this problem, but instead of it being an electron, we were told we had a proton moving at that velocity? Exactly. The kinetic energy would be different because it has a different mass. But that same kinetic energy would still convert into EVs the same way. Because this many joules is equal to 1 electron volt. Okay? And this is the difficulty with electron volts as opposed to joules. And that is that it doesn't matter how much mass it has. It's going to gain that much energy simply because of the charge it has and the work that the electric field does on that charge. Now, how fast that gets translated into, how fast it ends up going, that will be a function of the mass of the particle, but the total energy will just be a function of the charge and the potential difference. Is this clicking? Anybody else?
Yeah, whenever I type all of it in, I'm not getting the same answer.
What's the answer in the back of the book?
-1 volt.
Yeah.
I got 1.023 10 to the -38.
Okay, let's see. I may have written something down wrong. Did you 6 squared times 9.11 E31 divided by 2? I get 1.63. I get 1.64 times 10 to the minus 29 joules. Then divide that by 1.6022. Yeah, I get 1 times 10 to the minus 10 too. 1/2. I'm sorry, say again? You didn't multiply the 1/2 up here? Well, 9.11. Oh, I bet you. Yeah, that's it. It's right here. It's divided by 2 gives you that, and then you divide that by 1.602 times 10 to the minus 19, and I get 1.023 volts. So 1 volt. Well, you'd have to work that out based on whether you're accelerating or decelerating an electron. Yeah, in this one it said, all it said is what potential difference do you need to stop an electron that's moving that fast? It's a potential difference. So did it say negative in the answer? Then yeah, you're going to, because you're stopping an electron, you want it to go from a positive to a more negative potential.
So what are y'all getting for your kinetic energy? Because I can't get that. I'm not getting
Okay, I think right here it's, did you make this 6 times 10 to the 5?
Yeah.
And then square it?
Yeah, I swear.
And then multiply it by 9.11 times 10 to the minus 31?
Yeah, that's what I get. And then you divide that by 1.602.
Times 10 to the minus 19.
Right.
Is your kinetic energy of order 10 to the minus 19?
You get that, and then you divide it by 1. You gotta put that bottom number right there. It only divides that. It doesn't divide the whole thing. You gotta put it all in. But that's just your answer. When you put it in the form of times 10 to the negative 19th power, all that number has to be in there. Oh yeah, that's the order of operation.
There was a question on another one of the problems. 16. An electron starting from rest acquires 4.8 keV of kinetic energy in moving from point A to point B. How much kinetic energy would a proton acquire starting from rest at B and moving to point A? And then determine the ratio of their speeds at the end. Okay, you good?
Yeah, on that one.
Okay.
My other question is
Right. And it's pretty much the same problem. You've got an electron starts from rest and acquires 4.8 thousand electron volts, 4.8 keV in kinetic energy. How much kinetic energy would a proton acquire if it started at B and moved to A? That one you can answer that one without even touching your calculator. Well, it's not negative, but it's moving in the opposite direction, so it's going to acquire the same kinetic energy, 4.8 keV of energy. What's going to be the difference? The electron, because it's much lighter mass, is going to be moving a lot faster than the proton, having gained the same amount of kinetic energy. It's going to be moving a lot slower. And you calculate the speeds by, you know, the keV, you know they both have 4.8 times 10 to the 3 EV. You then, how many joules is that? Right here. 1 EV is 1.6022 times 10 to the minus 19 joules. So you would multiply that times 1.6022 times 10 to the minus 19 joules per EV. And that gives you both of their kinetic energies in joules. Then you simply solve for the mass of an electron. You use the mass of an electron, you use the mass of an electron to solve for the velocity of the electron based on that'll give you the velocity of an electron from that much kinetic energy in joules. Or in the case of the proton, you just use the mass of the proton to solve for the velocity of a proton. But the amount of energy is the same in both cases. It's 4.8 keV, or that many joules. So we got 4,800 EV times 1.6022 times 10 to the minus 19. 7.69 times 10 to the minus 16. Is that what you get?
Yeah. What did you get? How do you know what your velocity is?
Okay. We're getting there.
Oh, you
First thing you do is you do this multiplication and get the total kinetic energy in joules. You get 7.69 times 10 to the minus 16 joules.
Oh, wait, I get it.
Then you solve this for the mass, with the mass of an electron, gives you the velocity of an electron. If you solve it with the mass of a proton, it gives you the velocity of a proton. And you can compare their two speeds. The polarity came in when they specified in the problem that the electron got that much kinetic energy going from A to B, so how much energy would the proton get going the other direction from B to A? But energy is always positive. Kinetic energy is always going to be positive. If it were negative, what would that mean? What would it mean if we solved one of these equations and we found that an electron gained negative 16 joules? Say again? No. if it gained negative energy, it would be losing kinetic energy. What that would mean is that you did work on the electron to move it in the field, as opposed to the field doing work on the electron to give it velocity. So if you got a negative energy in this, it would mean you did the work or you added that much energy into the system. Okay? And that's that whole little confusing bit when we went back a week ago and we talked about the potential was defined as the negative of the work that was done. Now, before we go on, are there any more questions about the homework? All right, well. Then let's talk about electric potential due to point charges. And for the record, there should be a table in the front cover of your book, or somewhere in the front of your book if you have the paperback, the soft cover. There should be a table that gives you things like the mass of an electron, the mass of a proton, the mass of a neutron. Now, electric potential due to a point charge. Know that E, the E field vector due to a point charge is K Q over R squared. The voltage or the potential due to that same point charge is equal to K times Q over R to the power 1. Who remembers the units of an E field? Say again? Newtons per coulomb. And a Newton is kilogram, meters per second squared per coulomb. All we did here was multiply by meters. That gives us units here of kilograms, meters squared per second squared per coulomb. What's a kilogram meters squared per second squared? It's a joule, isn't it? Did anybody take notes last week about the units of a volt? Yeah, but 1 volt is divided by 1 joule per coulomb. So, you're right. The short answer is yeah, exactly. Work per unit charge, or joules per coulomb. That's the voltage due to a point charge. Now, this looks like it's exactly, maybe exactly what we need, because there was a lot of questions about what sign to use. Look at example 17.4. The potential due to a positive or a negative charge. Determine the potential at a point of 0.5 meters away from a 20 microcoulomb point charge and from a minus 20 microcoulomb point charge. If you're 0.5 meters away, what's the potential? Let's say we're here 0.5 meters down at that point. What's the potential here? K, everybody remembers, 8.988 times 10 to the 9 times Q, 20 micros, so it's 20 times 10 to the minus 6 coulombs, divided by 0.5 meters. No, not squared. We're not calculating E, we're calculating potential. This is for the E field. This is a vector. This is a scalar. And from the lab, we just did, what, yesterday, I guess. Who came up with a number yet? Anybody? That's what I got when I punched the numbers into my calculator. Let's try this again. We're 0.5 meters away from a positive 20 microcoulomb. What numbers did you type in? No, we're finding the potential. Yep. Now, so we write this as 3.6 times 10 to the 5 volts. And it's a positive potential. What if we were the same distance away from a negative 20 microcoulomb charge? We'd have the same potential, but it would be negative. You'll notice that's pretty big voltage, isn't it? Y'all work with electricity. Look what happens when you plot potential as a function of distance. The closer you get to that positive charge, the higher that potential goes. The closer you get to a negative charge, the lower that potential goes. on K is 8.988 times 10 to the 9. And we're not looking for E, we're looking for V, voltage. So do not divide by R squared, divide by R. And Coulomb, the Q is 20 times 10 to the minus 6.
Oh, well, I did it in my mistake.
Oh, that'll give you a whole nother answer.
Yeah.
That'll give you a whole lot more voltage.
That would be milli.
Now, this is another important thing here. This E field that we calculate is a vector field. Okay, so when you use this expression to calculate, you're actually calculating a vector. You could take a point charge, put it out in, and then just pick points in space and calculate the vector for each one of those points in space. And this is the equation for a vector field. If you have 2 or more point charges, you go to any point in space and you calculate the vector of E field from each one of the point charges, and the total vector E field at that point is going to be the vector sum of the E field from each one of the particles. Okay? You have a particle here, you have a particle here, you have a particle here. You calculate the field here. This one gives you a vector this direction. This one gives you a vector in this direction. This one gives you a vector in this direction. And then you get the vector sum of all 3 of them. And that would be your total E field vector at that point in space. You can add up as many point charges as you need to in order to calculate that all of the constituent vectors of this vector sum, and you will end up with a final vector at that point in space. And you can do that for as many points in space as you need to. Plot out that whole vector field. But this, our potential, is not a vector. It's a scalar. So if we're calculating the potential at this point in space, it's just a number. It's still the sum of the potential due to that point, plus the potential due to that point, plus the potential due to that point, so that you end up with a sum of all of the contributing potentials, but it's just a scalar sum. Just add the 3 numbers together, and that's your potential. We just did this in lab. You had a point charge here, you had a point charge here. If those 2 point charges are the same, you go to the if they're but opposite polarity, the potential here is some positive value. Potential due to that one is the minus value. And the 2 will cancel out, and you'll have a straight line here that's 0 volts. Because every point on this line, as long as it's the same distance between the 2 charges, they're always going to add up to 0. See how that works? Let's work an example. Actually plug some numbers into the calculators. They gave us an example here in the book of 2 point charges, plus 50 microcoulombs and minus 50 microcoulombs, 26 centimeters apart. This isn't a problem. This is just an example in the book. Figure 1710, example 17.6, page 480. Now, and I'm going to just trust them, some of their numbers, but they say if you go to a point right up here, 30 centimeters above the positive point charge, then you are, in fact, 60 centimeters away from that one, from negative. And if you go the same distance up here, you're going to be 40 centimeters away from both of them. Okay? So, let's calculate the potential at both of these points, A and B. Well, the potential at A is going to be K times 50 times 10 to the minus 6 coulombs divided by 30 centimeters is what? 0.3 meters, right? Plus K times minus 50 times 10 to the minus 6 coulombs divided by 60 centimeters or 0.6 meters. So that's going to be 1.498 megavolts, or 1,498,000 volts. That one will be 8.988 times 10 to the 9 times minus 50 times 10 to the negative 6 coulombs divided by 0.6 meters, or minus 749,000 volts. So you add the two together, and you end up with voltage at A, or the potential at point A, is equal to 749,000 volts. But now what about B? Sorry, say again. Everybody getting the same numbers? We're not getting anyone not getting the same numbers? Ten to the negative. You get 1,498,000. Did you? Clear everything out. Start with a clear register. 8.988 times 10 to the plus 9. You used the negative exponent on the K. That'll change your answer. Has everyone else done y'all all get the same numbers? Okay, now let's do it for voltage or the potential at point B. Again, we have K times 50 microcoulombs divided by now 0.4 meters plus K times minus 50 microcoulombs divided by the same well, not the same 0.4 meters, but by 0.4 meters. Say again?
How did you know that they were both?
Oh, because I trusted that the book got it right.
Oh, it's not the middle.
Yeah, it's equidistant, so it's going to be the same. This one gives me plus 1,123,500 volts minus, because that's a negative, minus 1,123,500 volts, 0 volts. And like we said, anywhere on that line, as long as the point is equidistant between the two charges, it's the same distance to either charge, anywhere on that line, it's going to sum to 0. Over here, we were at a fairly positive voltage of 750 kilovolts. What would happen if we came over here and calculated the potential here above the negative, 30 centimeters above the negative? It would be negative 750 kilovolts. Because then it would be this point that was 60 centimeters away for a plus 749,000 volts, and the negative charge that was only 0.3 meters away for the minus 1.498 megavolts, giving you a net negative potential. Hey, are there any questions?
Let's be on the test.
Most definitely. I don't know about that problem, but this material will be on the test. What I want to know is, do we have time to cover a dipole? I'm sorry? Yeah, that's what I'm looking at, and I don't think I'm going to do the dipole in 1 minute. So I've got to do the dipole, capacitance, dielectrics, and storage of energy on Friday. Say again? What is it says Monday? Then yeah, we will have an exam. Do you want to push it off until Wednesday? What about everybody else? Would everybody else like to push the exam until Wednesday? Get a chance to get to work some of these exercises? Okay. We can do that.
What homework problems are due? Oh, no, okay. They're all didn't know they were putting
Thank you. You too. You too.
You guys have ECD?
I don't know, I think all my name.
Thank you.
So like, I gotta get some of my homework.